All right, so we're going to give this a try. So I'm going to work through the Unit 1 FRQs for you. All right, so here we go. For number 1, Part A, in terms of atomic structure, explain why the atomic radius of potassium is larger than that of sodium. There's a couple different choices you could have put down. You could talk about the valence electrons of potassium are at a higher energy shell than that in sodium, or the outer orbitals have a higher principal quantum number in potassium than in sodium. Remember, quantum numbers are the energy levels. So this is quantum number 1, 2, 3. Or you could have talked about the valence electrons are less attracted to the nucleus than those in sodium. And that's all about the shielding. Remember, the more electrons you have in between the nucleus and the protons and those valence electrons, the more shielding there is, the less attracted they are. And that leads us into the next question, which was talking about, in terms of atomic structure, explain why the first ionization energy of potassium is less than that of calcium. Well, if you look at it, the first ionization of potassium is less than, potassium is less than calcium because the electrons removed from potassium are less attracted to the nucleus than in calcium because of fewer protons in potassium. Fewer protons, less positive charge, less attraction. For C, potassium forms a compound K2O, which is an ionic compound. Identify another element that will form a brittle ionic compound. Well, anything else from group 1. Lithium, sodium, rubidium, cesium, and francium. So anything else from that, with the exception of hydrogen. Okay, and then the final one was about being able to determine the compound for K2O also exists, K2O2. Chemists can determine the mass of potassium in a sample that consists of either pure K2O or pure K2O2. From this information, can the chemist answer the question of which compound is in the sample? Yes, he can, because if the mass of potassium is calculated, the percentage mass of calcium can be calculated and the compound identified. So for instance, the mole ratio of K2O is 1 mole. For every 1 mole of K2O, there's 2 moles of potassium and 1 mole of oxygen. Here's your molar masses. So the percentage of potassium in K2O is 83%. Doing that exact same thing, the percentage of potassium in K2O2 was 70.96%. So you could actually figure this out. So what I was just looking for is yes, and about the percentage. If you can calculate that, you can calculate the percentage mass or percentage and also the compound. All right, so number 2. Number 2 was talking about using a mass spec. So you have a mass spec graph, and you had percent abundance on the y-axis, and you had atomic mass on the x-axis, and it was a sample of a pure element, and it asked you how many different isotopes were there. So there were 3 different isotopes, one with 24 atomic mass units, one with 25, and one with 26. Thus the 3 different bars. And you need to, use that information to determine the average atomic mass of the element? Yes. You use an average weighted average. So you have 0.79% abundance times 24.10 times 25.11 times 26. And you get the weighted average atomic mass, which if you calculate that, it's pretty darn close to magnesium, which is at 24.31. It is also the most common or prevalent of the isotopes at 24 AMUs. And so it was magnesium. And then the electron configuration for that, using our good old friend, the periodic table, 1s2, 2s2, 2p6, 3s2, magnesium. So hopefully they get you taken care of. I will post this and do the same thing for the Unit 2 free response questions here in a day or two, okay? Look forward to talking to you guys hopefully tomorrow during office hours. And until then, take care, stay safe, stay home, and stay healthy.